You can hear me well enough? Good. All right. So, good afternoon, everyone. For those who don't know me, my name is Matt Ricci, and I'm a postdoc at the Data Science Initiative. I'm very pleased to welcome you to our first post Thanksgiving Data Wednesday. We've had an excellent lineup of speakers so far this year, a trend that's going to continue through future sessions, which you can find on the DSI website, including talks by Marta Gonzalez of Berkeley, who will speak about data science for city planning, and by Robert Greist from UPenn, who will present on some new work in topological data analysis. Today, we are very lucky to have with us Professor Brenden Lake from NYU. Brenden is Assistant Professor of Psychology and Data Science at NYU, where he studies computational models of commonplace cognitive abilities in machines and minds. Today, his talk is entitled uh, Learning to, I think I might have a mistake here. Is learning through the eyes of a child? Yes, learning through the eyes of a child. So now, will you please join me in welcoming Brenden Lake?
Thank you very much for inviting me. And this is new work, and it's my first time giving this talk, so I'm looking forward to feedback, and feel free to ask questions as we go. And I had help from two amazing postdocs in putting this talk together. And their names are Amin Oran and Wei Keen Vong. And they're the leaders on the work I'm going to tell you about. Amin in particular is responsible for the majority of what I'm going to talk about today. And Amin is also on the job market this year. So if you know the right position for him, be sure to get in touch. I'll jump in. The last several decades have brought about an increasingly rich picture of the infant mind. Decades ago, we thought the infant mind was, infants were relatively just passive observers of the world. And now we understand that there's a lot of sophisticated cognition going on in their minds from the earliest stages, and they build sophisticated models of the world. So here's a chart from the DARPA Machine Common Sense program, which outlines a wide range of cognitive milestones and the rough ages that they are achieved in development. So it spans from 0 to 18 months in this chart, and the different milestones are organized by different core domains. So there's the domain of objects and agents and places and mark when we can estimate from the empirical literature that infants begin to have a sense that objects have depth, or that they move separately from one another, or that they change motion when they bump into another object, and so on. Just to paint a small piece of this rich picture of what the infant mind is capable of. And I just wanted to highlight a couple of these milestones in a bit more detail. Within the first few months of life, so here I'm really talking about 2-month-old, 3-month-old, 4-month-old infants. Infants have meaningful expectations about the behavior of objects in particular. They know that objects persist, and that if you show an infant a screen that moves back and forth, and then you place an object behind that screen, then when that screen starts to move, they expect that the screen will hit that object and be unable to move, as opposed to just going right through it. So they understand that objects persist even when you can't see them, and also that objects are connected if their visible parts move together. So in a classic experiment from Kelman and Spelke, you have this, what looks like 2 rods moving behind an occluder, right? Or at least these 2 pieces of perhaps 1 object, perhaps 2 objects, but they're moving together. And then when you take away the occluder, infants expect there to be a single object as opposed to 2 objects moving together. Also, very early in life, infants have sophisticated representations of other agents, and that agents act efficiently, and that if you have an agent jumping over an obstacle in order to reach a goal, if you take away that obstacle, infants expect the agent to move in the most efficient path in order to achieve the goal, as opposed to reproducing the same behavior as before, or that agents have goals that if you see an agent repeatedly reaching for the same object, and then you switch the location of that object, the agent will do something else. They will not repeat the same action, but instead they'll actually go find that object where it rests currently. So again, young infants within the first few months of life have sophisticated understanding of many things, including impressive abilities for categorization and word learning, which are the topics that we're going to focus on today. that young infants can discriminate common visual categories by 3 to 4 months. They can discriminate, say, dogs for birds, or even 6-month-olds can identify some objects by name. If you prompt an infant by saying, look at the mouth, so this is well before they're speaking, and they'll spend more time looking at the mouth than, say, the apple, or more time looking at the juice than the nose. It's just suggesting that they're beginning to learn the meaning of these words. So this brings us to the key questions at the heart of the project I'm going to tell you about. And these questions are really some of the oldest ones in psychology and cognitive science and philosophy. What is the origin of knowledge, or this early knowledge that the human mind has? How much can be acquired through generic learning mechanisms applied to sensory data? And how much require more substantive innate inductive biases? But of course, this is a modern reformulation of the nature-nurture question from antiquity. And of course, we're not going to be able to resolve such a question to its full extent, but instead to provide a complementary lens to the empirical work going on in cognitive development that tests younger and younger children to try to understand, what abilities emerge at which times, and in which order, and what might be innate and what might be learned. But instead to talk about what is learnable in practice when we apply large-scale modern machine learning algorithms to a representative sample of the actual experience that children get when they're developing. So what can we learn, and what is more difficult to learn, or what can we not learn unless we add stronger inductive biases to our models? There are two ingredients for addressing learnability in this way as we're formulating it. And that first ingredient is raw naturalistic input data. In particular, head-mounted cameras attached to developing children, so we can get a sense of what the world looks like from their perspective. And in particular, we're using this new data set from Jessica Sullivan and colleagues, which is on site archive, called SayCam. It provides an unprecedented view into what the world looks like from a child's perspective. And also relatively generic machine learning models, that's the other ingredient. But when we apply relatively generic machine learning models, and by that I mean neural networks with relatively general inductive biases, just like a convolutional net for computer vision problems, when applied to that data, what are we able to learn? And since we're talking about learnability in principle, we're not going to restrict ourselves to psychologically plausible learning algorithms. So the way that the network or the algorithm may learn is not supposed to be representative of how children may actually go about learning the same thing. We want to know what is learnable given the data and a powerful model. For this talk, our focus is on categorization, as I mentioned, and we want to know about the high-level visual representations and how do they emerge from one baby's experience. So our approach is to, as I alluded to, is to train machine learning models on a strict subset of one child's experience. So there's been other work applying machine learning to realistic head-mounted camera data from kids. Usually it's collected in short clips from a bunch of different children and aggregated together. We don't want to do that. We're just going to train a model through the eyes of one child. So the model only will see the data that one child saw, and ensuring that it doesn't see anything additional that wouldn't be available to a single developing baby. In addition, the models are trained self-supervised in that we want to provide no additional supervision that also the child does not get. There's going to be no explicit labels in that sense beyond what the data gives itself. And also, as I mentioned, our work is going to focus on categorization and word learning, which might map on to the acquisition of language or some of those early perceptual discriminations or the acquisition of perceptual categories that I mentioned. The data set that we use is called SayCam from Sullivan et al. And this is the paper, so I encourage you to check it out if you're interested in reading about it or using it yourself. And we're just incredibly grateful for this resource and that was made public, and I see it as a tremendous contribution to science that we and others are only beginning to scratch the surface of like the richness that is available from this type of longitudinal data from individual kids. But here are more specifics of the data set. It's longitudinal audio-visual recordings over the course of 26 months. And although it's audio-visual, for the first part of the talk, I'm just going to tell you about work we did with just a video. And there's only 3 babies in the data set. So as I mentioned, it's not hundreds of babies with short clips. It's only 3 babies that were recorded roughly over 26 months. And it wasn't continuous. They didn't wear the head cam every day. They just wore it for 1 to 2 hours per week over this 26 month or a little over 2-year period, right? So we don't know everything they saw, but hopefully it's a representative subset of the type of experience they got over those 2 years of development, starting at 6 months and ending at around 32 months. And the baby with the most data, baby S here, has 221 hours, and baby Y had 140 hours. You can get a rough sense of what that corresponds to. It'd be about 2 to 3 weeks worth of awake time for a child if you were to lump it all together, but again, it was spread out. So I'll show you an example of what the clip looks like. So this is one of the older clip from one of the kids when they're 32 months, so they're a little bit more able to move around and play and so on. And you're not hearing the audio here, but you can imagine the 6-month-old is not doing nearly this much. It's mostly staying much more still and sort of moving their head around and so on. Okay. Oh, and just to get a sense of what's in there, the parents tried to make it representative examples of what the child would see, and just to put the camera on 1 to 2 hours a week as they're going about their daily activities. So I'm going to tell you about a NeurIPS paper that Amin, as I mentioned, the postdoc in our group, is presenting at the NeurIPS conference next week. And that paper is called Self-Supervised Learning Through the Eyes of a Child. And here, Amin introduced a very simple self-supervised learning algorithm. The algorithm was the focus of the paper, but it did seem to perform better than other state-of-the-art methods that we tried for this particular problem. And this algorithm is called temporal classification. It's extremely simple. You take this long stream of videos and you chop it up into segments, and you call each of those segments a class. So the first segment is going to be class A, the second one is class B, and so on. And then you train a deep neural net to try to map a frame. So it gets a frame from one of those videos and then tries to map it to the corresponding segment chunk, right? So is this in segment A or in segment B, and so on. And the hope is that it learns some interesting invariances over time, like semantic invariances that if it's learning to map frames from video to the same label, that they're going to capture some high level structure because some of that semantic information doesn't change as quickly over time. In terms of the hyperparameters, this algorithm has a hyperparameter for the sampling rate. It picked, just in this case, 5 frames per second, the segment length of about 5 minutes, each of the classes, about 5 minutes worth of video. And there's also some data augmentation, particularly for color and grayscale. So this leads to a few thousand classes that this network is trained on just in a self-supervised way, because it's not using any labels, it's not using any category labels, it's just sort of chunks up the video in time. And it's also worth mentioning that these chunks are relatively naive, but there's also a lot of work in cognitive science on event segmentation, what makes a coherent event. And if you imagine you had a little bit of an inductive bias that chopped up the clips into cognitively meaningful events, it could potentially be a stronger model.
Brenden, can I interrupt for a second? Sorry,
Yeah.
I missed. How do you define the segments? Is it kind of a set recording around an object? So what defines a segment here?
It's quite naive. So we just took the 220 hours or lined it all up in one long video and took a chunk every 5 minutes.
Oh, I see. So it's a fixed. Okay, good. Thank you.
Yeah, that's all it is.
There's no manual segmentation where. Okay, so there could be potentially more than one object within a sequence, right?
Definitely.
And changing objects, right?
It's 5 minutes, right? I mean, usually it's in the same location of the house and so on, and the same types of objects are present, but it's not going to be a one-to-one correspondence of labels to objects in any sense.
Thank you.
Good question. Okay, and we compared against various alternative models. I represented of some of the state of the art in self-supervised and supervised learning and neural networks, in particular image-based momentum contrast, or the MoCo algorithm, which is relatively new from Kai-Ming He and colleagues. And the idea behind MoCo is one of these contrastive methods. So it learns a visual embedding such that transformed versions of the same image are mapped to nearby points in space. So if you can see my cursor over here, you would take this image of a dog on the left and transform it in 2 different ways, and then train a neural network to form an embedding of each of those different transformed versions. And you want those embeddings to be similar because they have the same content. So you want those two, there's an attractive force between those 2 embeddings. But then say for this picture of a couch, you'd want that embedding of those transformed images of couches to be far away. You want those to repel the ones from the dog. So you don't have any category labels here. You're just merely transforming images and trying to push the transformed versions of the images together. But that's a state-of-the-art method. We also compared, we're using videos though, that's just with static images. So we modified it to take into account the temporal structure of videos. So we not only do this, but also take neighboring frames in the videos and try to give them a similar embedding. Another approach is we took a strong ImageNet pre-trained model from the same architectures. So for all this, for this paper, we used MobileNet v2, but we also have done this with our ResNet 50, and the results are pretty similar. The ResNet is a little bit better, but all these have the same architecture. So we take the architecture trained on ImageNet supervised, and we also have a random network, and also a shallow baseline histogram of Gaussians, more of a classic computer vision baseline. And we want to see how these different systems would compare in terms of trying to make basic visual discriminations. The foreshadow that temporal classification model is going to do better than the others. And I'll explain how we're going to evaluate these models. The first evaluation is object recognition using what we call the labeled S set. So S being one of the babies. And this data set is not labeled in sort of the sense that this image corresponds to this category label, but there's some very weak labels that annotators went in and marked what the child was looking at least a guess, at various points in time. And we used that to sort of bootstrap that to get a labeled set, which we then manually verified. Or we took 26 developmentally appropriate classes that were repeated in the data set. Now this data is completely different than what you get from ImageNet. It's not balanced, right? It's highly skewed. You see like toy over there has a very high frequency, and floor and ball and room are very high frequency words or high frequency objects. They're not really words. We're not using any language here. And couch and basket greenery are a little rarer. But it's not that you get this uniform sampling of toys or a bottle and so on. You see the baby's bottle, their main bottle, you see it over and over again, right? So you get some objects with lots of different views. And Linda Smith's group has done some really nice work quantifying a lot of the differences of the naturalistic statistics from what babies actually see compared to like what we use in their computer vision benchmarks, but it's very different. And here's an example of some of the frames with cats and cars and cribs and sand and so on. And these were all developmentally appropriate categories, and it led to a labeled set of about 58,000 frames, which again, we're not going to train with, we're going to use it for evaluation. The second evaluation is object recognition using a toy box data set from Wang et al. And this is nice because they're toys, so again, developmentally appropriate. And there are 12 unique simple classes like airplane, car, ball, cat, and so on. They're all toys being held, and it was a video data set as well. There's 30 exemplars of each of the different classes, so 30 different toy airplanes and toy cats and toy balls. And there are 11 different transformations. So in the videos, they have certain types of rotations and translations for each of the different toys. And we're gonna try to see if we can recognize these different classes as well. Okay. To evaluate the models, we use a standard protocol in self-supervised learning, and that's shown here, which is that we pre-train the model with the self-supervised objective, and that's shown there in purple. We freeze the features, And then we're just going to try to train a linear classifier shown in yellow on top. And the reasoning here is that if we have good high-level representations, we can discriminate behaviorally relevant categories using these features. So we're not going to learn the features from the labels. We're just going to see is, given our fixed frozen features, is there a linear combination? Is there a reweighting of those features that will allow me to distinguish between cats versus dogs, or between feet versus hands, and things like that? And it just, again, to emphasize, we train the model through the eyes of just one child. So the network is only going to see data that one baby actually saw. So let's look at how the different models perform on this labeled S set. There's 26 different classes, but it's skewed. So if you look at the majority class, if you just always guess the majority class, that's that dotted line there around the 12%. And on the y-axis is the top line accuracy. And TC is the temporal classification model. And you do about 60, a little bit, 62% correct if you train the TC model on the world through the eyes of baby S and then test it on this labeled S data set. You can also do okay if you train it through the eyes of some other babies, baby A or baby Y, and then that provides sufficiently rich features in order to discriminate the classes that I was showing you on this previous slide. As mentioned, temporal classification performs better than some of these standard contrastive learners, even when modified for video. So we have the MoCo temporal version, which is a little bit better than the MoCo image version, which is very commonly used. And we even outperform a strong ImageNet model trained supervised, right, on ImageNet. You can do better from the self-supervised model trained through the eyes of the baby. And finally, as I mentioned, we looked at a randomly initialized network and also a shallow model, and found that they don't perform well. So it highlights the power of having a deep neural net trained through the eyes of a child in order to discriminate these behaviorally relevant classes. The one concern is temporal correlations in the data, is that the label data is relatively densely sampled. In that here are 36 sequential frames from the cat class. If you take everything in the cat class, that label set, and line it up, you see that like there's a lot of similar frames, and thus it's possible that some of these are in the train set, some of these in the test set, and it could just be a relatively simple transformation from one to the other. But you only have this linear model, and the control model suggests that it's not easy to make this generalization unless you have powerful features. But we wanted to make a harder version of this task in order to reduce some of this temporal correlation. So we took this clip here, which was at 1 frame per second. We did a 10 times down sample, so now it's 0.1 frames per second. And this is the same clip, and you can see that the frames look quite a bit different, unless there was a point in the video where the child was staying relatively still and looking at that cat. And thus we reran everything with just a frame one every 10 seconds, and found that the results are very similar. It's still the same ordering of the models. The accuracy is a little bit lower, but you'd expect that because it's less data. And otherwise, as I said, the ordering of the models are relatively similar to, or exactly the same as before. Next, let's look at the toy box data set, which tests whether, again, there are features that will allow us to discriminate common toy classes. And this is really out of domain because this is not from the same videos that it was trained on in any way. So the simplest task involves generalizing to new simple transformations of an image. So if you take these videos and then you split them by ID, you have to make simple transformations from, say, the plane in this location with this angle to the plane in a slightly different location with a different angle. That's what happens if you do an IID split. And if you do this, you can get about 75% accuracy for this 12-way classification problem. And the ordering of the models is relatively similar to before, with the temporal classification model the best of the self-supervised algorithms, and then an ImageNet pre-trained supervised model is better in this case. But we also ran a version where we have an exemplar split, where now we're going to it's much more challenging because the network would have to generalize from a few examples of an airplane to other toy airplanes that it has never been exposed to. And on this task, which is more difficult, the models are still well above chance, suggesting that the visual representations are enough to generalize to new exemplars of common classes. So you can get a new airplane based on a handful of examples of other types of toy airplanes. We also explored some hyperparameters of the best model, in particular the temporal classification model, and found that if you increase the sampling rate, so you essentially have more data, you do a little bit better in terms of accuracy, which isn't the big surprise. We also varied the segment length. So what is the right length of a segment to form one of those temporal classes? You could have very short, 18-second segments, or what we used was a 288-second segments, about 5 minutes, and found that you get better accuracy as you increase the length of the segment, suggesting that there's important semantic invariances over segments of up to 5 minutes, and then after that it started to saturate. And we also looked at the effect of data augmentation and found that it does help, but it's not essential. You don't need to do data augmentation to learn meaningful features. We also looked at some qualitative results. First, one observation is that individual features that the network learns do not correspond one-to-one to meaningful high-level visual concepts. So here are just two of the highest level features that were learned self-supervised. And what's being shown is basically the attention of that feature for what it's responding to for each of the different frames of the video. And you can try to make out what this feature might be sensitive to. And it seems clear that it doesn't correspond to just a single high-level concept like doll or toy and so on. That it does seem to be like broadly responsive to a variety of different types of visual stimuli. I'll just play this for a few more seconds. So there does seem to be this distributed code at a high level. And we wanted to quantify the selectivity of the features using a class sensitivity index metric that Marcos proposed a couple of years ago, which is inspired by metrics used in neuroscience, where the idea is we want to know, is a feature class selective? So for any given feature F, we measure the mean response of that feature for all the different classes in the data set, right? So how much does it respond to the cats versus the feet versus the hands? And then we take the average response to all the members of the most active class, and then subtract off the average response to all the other classes. And then we normalize that so it's between 0 and 1. So if the feature was perfectly selective to just one class, meaning it responded to cats and nothing else, then you'd have a value of 1. But if it's equally selective to all the classes, then you have a value of 0. And what we find is that as I pointed out in the video, the features aren't highly selective. That if you look at the y-axis is that class selectivity index, and blue is the SACAM model trained self-supervised. For those 26 different classes, in most cases, and this is looking at the different layers of the network. At the earlier layers, it's a little less selective, more selective at the higher layers, but somewhere between 0.2, 0.4 on that class selectivity index. But interestingly, an ImageNet trained model trained on ImageNet and then looking at the selectivity to ImageNet classes, so it's trained supervised, it's not any more selective than the self-supervised model for individual classes. So if you look at the orange here is an ImageNet model with the same metric, as I said. So even a supervised model doesn't seem to learn these like grandmother cells that respond to just one particular class. Instead, it must be some linear combination of the features that allows it to just discriminate the various classes. So that's the key question. Can we construct high-level concepts out of a simple combination of individual features, right? Can we get a cat detector from just a recombination of those high-level features? So this is what an ImageNet supervised model must be doing, because it doesn't have these highly selective features. So it must be recombining them at that highest layer in order to build a classifier. But what I'm going to show you here is a class activation map, where the basic idea is that you take all of the features at the highest level and see where they're responding in the image, right? So you basically make this attention map for each of the different features, but not all those features are relevant for detecting cats. So you take the cat output up from the linear classifier, and then you reweight those attention maps based on their strength in the cat classifier. So the features that are more responsible for cats get a stronger weight, and you can build one of these aggregate maps that basically saying for the cat detector, where is it responding and where is it responding in the image. And what you see is that you can actually get a sort of emergent a representation of a cat, or in the sense that the model, when it thinks there's a cat in the image, is looking at the right place in the image. So I'll play this video. So it generally highlights the cat, and when it looks away, it responds less. And then there's going to be a nice ablation here where the toy shows up, it kind of blocks out the cat, and the particular activation map gets quieter when the cat's being blocked by the toy, which suggests that it really does seem to be selective to cats. Here's another way of seeing the same thing. There's actually a few different cats in this household, and there's some cats in books and so on. And this is looking at different frames from that cat set and looking at again the class activation maps. And here we're going to threshold it at a certain value so you can see if it's responding more selectively or not. And in this case, it tends to, for the images with cats in it, it tends to look at the right parts of the image, the parts with cats. And then for the images that don't have a cat, first of all, this activation map is a lot less active and also is much less structured. And here's the same thing with computer, which is also a relatively highly selective class compared to the other ones. And again, with these class activation maps, you can see it tends to look at reasonable parts of the image when making this decision that there's a computer in the image. That's exactly what you would like to see if you had a good classifier for computers. Interestingly, there are some ambiguous images in the data that don't really have a collect label. So me and mine, the data set for some of these, which are interesting because the labels aren't mutually exclusive, right? Some in the labeled S set, there are both cars and roads, and sometimes you're going to have an image that's both a car and a road in it. But this could be another way to probe what is learned through the eyes of the child of this case, where we present this frame to the network and see what its decision is. In this case, that image at the top, it was classified as a car, and then look at what part of the region was responsible for its decision, and it's actually focused in on the cars on the image rather than the other pieces. Same over there in the middle, foot versus hand, that red thing that's a little hard to see is actually red socks, so a foot, and there's also a hand in the bottom. And the network selects foot. It's actually looking at that part of the image as well. For chair versus table, this frame has both a chair, like the baby's chair, and a table, and again it responds chair, and the region of the image responsible for that decision is over there on the left. So if it picks cars, generally looking at the cars again, suggesting that these interesting high-level visual structure is being applied. What can we conclude? This is the interim conclusion for the first part, and then I have a shorter second part of the talk, which I'll tell you about next. We showed for the first time that generic models can learn high-level visual representations through the eyes of a child. And these representations can support the same types of category discriminations observed in infancy, like being able to discriminate the difference between dogs and birds and so on. In terms of limitations, the network was trained on just a small subset of a child's experience. So 2 to 3 weeks worth of wake time compared to 26 months, which is what the child actually got in that same amount of time. So it is, although unprecedented to look through what an individual child sees, it's not all the experience, it's just a small subset of experience that they get. Of course, this type of exploration ignores the embodied active component of learning and development, which is crucial. The child, to some extent, is responsible for collecting their own data actively, right? They can choose what to look for, they can choose what to touch, and so on. And all of that is being missed from this type of modeling, which is extremely important. We're ignoring the spoken language input and just doing this from the videos. And also we're relying on trained decoders to help interpret their learned representations rather than relying on more direct behavioral outputs. So in the second part, we're going to address a couple of these limitations. And this part is really about word learning. And we want to know, how can children learn the meaning of words from the noisy, naturalistic raw inputs that they actually see? So here are, as I mentioned, there's audio along with the video, and for some of it, it's been transcribed. And here I'm grabbing some of those utterances transcribed with the frame that they're timestamped with. And you can see that it looks something like, you see this block, the triangle, it goes in, boop. This is the type of exposure that the child's actually getting when they're learning words. And we're going to see how it might be possible to learn words from it. So in this case, in addressing the limitations, we're now going to use the spoken language input, and we're not going to rely on those trained decoders to figure out what the representations consist of, but instead we're going to actually learn at how a network might ground the meaning of the word in terms of the visual input. So here are some of the key challenges to word learning that show up here in a very vivid form, in that the individual utterances are ambiguous, that children must engage in a type of cross-situational learning in order to learn the meaning of words. So if you look at any given utterance, right, like over there on the right, all these cars suggest there are cars in the image, but if that's all you had and you didn't know anything about cars, you wouldn't know if cars referred to like the white marks on the road, the trees, the actual cars, the sidewalk. It's not clear. The utterance is ambiguous. So to learn the meaning of words, it requires aggregating information and tracking co-occurrences over time, and noticing that when I hear the word car, it tends to occur with this type of object, right? Or this type of visual structure. So these individual utterances are ambiguous, and you can see that across these 4 examples, like, yeah, now we're heading home, look at the cars on the street, yeah, all these cars, you have to sort of aggregate that information over time. And just to highlight this a little bit more, this cross-situational word learning problem is defined as the ability to learn word-referent mappings across ambiguous scenes and utterances. And this is actually something that babies can readily do. There's been a lot of work in cognitive development on cross-situational word learning. And for instance, Smith and Yu showed that 12 and 14-month-old babies can learn cross-situational mappings if you show them clean experimental stimuli. So for instance, you might show a scene like this with 2 objects, and then you get a caption, Dax Toma, but you don't know which one's the Dax and which one's the Toma. And then you get another scene, and this one is labeled Toma Gloop, right? And if you remember and aggregate this information over time, you might see the co-occurrence pattern and realize that Toma co-occurred with the green object both times, and that might be the meaning of Toma. We also, in a different work by Wei-Keen Vong, one of the postdocs I mentioned at the beginning, he showed that neural nets trained with self-supervision can also do this type of cross-situational learning when trained on this clean experimental stimuli. But now we're going to bump this to the real world and see if some of the same things are possible with raw naturalistic data through the child's eyes. So that's one challenge. And another challenge is that many utterances are short and uninformative. You actually look at what children hear, it's a lot of yeahs and ums, and not really that helpful for learning the meaning of object names. And another challenge is that the meaning of an utterance often depends on the utterances in the same video, which are not currently modeled. So it depends on the previous utterances. You say, oh, look at that over there. It's just like this one, right? It's impossible to know what that means without knowing what you were talking about right before. And in the learning that we're going to do here, we're just going to treat these utterances in isolation along with their corresponding frames. So it doesn't get that structured. Okay. So here are some specifics of the data set. We're going to look at, I mentioned, multimodal learning with SACAM, and so far, only one of the 3 kids, a baby S, has sufficient amount of speech transcribed in the corpus, about 30% of the videos, 60 to 70 hours. So we used that, and we only used the child-directed speech from either parent. So we don't use the baby's utterances, we just use the utterances to the baby. And this resulted in a data set of about 35,000 utterances from 360 videos that we can train on. And for each utterance, we extracted just a single frame of the video that's time-stamped to when the utterance, by a labeler, when the utterance was made. But it's noisy, so it's not always exactly when it was said. Sometimes the object is out of view, and it's highly cross-situational in the ways we were talking about. So the training data is these image utterance pairs. And here's what the data actually look like. So here's like a longer version of the clip that I showed you in a couple of slides ago. So yeah, now we're heading home. Look at all the cars on the street. Yeah, all these cars. It's very exciting. Yeah, now we're going through the basketball court and so on. So this type of narration that the young baby gets. And what can you learn from this? But here's the model architecture we're going to use, and we're going to borrow ideas from other self-supervised learning models, particularly from some of the references listed on the bottom of the slide. And again, it's going to be self-supervised. And what we need now is an image encoder that's going to look at the frame and build a representation of the image. And we're going to pre-train this on SACAM. We're going to use the self-supervised model from part 1. We're going to use that as the pre-trained model for part 2, right? Because it was learned from just the raw video and no labels. And now we're going to see if we add in some of those labels from the transcription, can you pick up the meaning of some of the words? Now for the language encoder, this is going to build a representation of the utterances. So for the language encoder, we either use just simple word embeddings. So each of the words are treated in isolation, like a bag of words, or an LSTM to try to be able to resolve the word sense disambiguation. In some cases, the words are ambiguous based on the surrounding words. So that we have an encoder for the image and encoder for the language. And how is the network trained? Well, in essence, the encoder of the image spits out this set of vectors V, which is an embedding of the visual representation at different spatial locations, so different parts of the image. And for you, from the language encoder, this is going to be an embedding for each of the words in the utterance. So we have a set U and a set V, and basically we need to look for correspondences. So how the network is going to be trained is we would pass in one utterance with its frame, and then copy the network and pass in another utterance with its frame, that's shown over there in blue, and we get a representation V prime and U prime for that other utterance and image. And then we're going to calculate the similarities between the sets of vectors, with the goal of trying to make the matching pairs more similar. So we want V and U to be quite similar to each other. And we want V prime and U prime to be quite similar to each other because those captions or utterances are matching those particular frames. But at the same time, we want our repulsive forces shown here in red. So we want to make sure that if you pair V and U prime, that they're far apart from each other in space. Or U and V prime, that again, those would be far apart because there are mismatches between that image and that caption. So by doing this shuffling, we want to put the matches close together and the others further apart with the similarity metric. What are we going to use for the similarity metric? Well, we're going to use this function over here, and just to unpack it a bit, it's basically saying for each of the words, we're going to pick a spatial location VJ in the image that has the highest similarity or the highest inner product. So we're basically going to try to find or localize where in the image it best corresponds to each of the different words UI. And then we're going to compute the average similarity, so the average of the max, by taking the average over each of those different words. So this assumption that we're working with is that each word should be reflected in the image. You must find some signature of each of the words in the image, but not every visual feature needs to be described, right? So each word should have some grounding, which of course isn't true like with a lot of words, but nevertheless, it's an assumption we're working with here. But not every visual features can be talked about. So that's the similarity function. And how do we evaluate whether any of the words are learned successfully? Well, we're gonna use the same evaluation set as before from labeled S. And we're gonna build these little 4-way classification trials, which are representative of how children are tested in these cross-situational learning experiments. So we're gonna basically instruct the network to find the ball, and then we're gonna give it 4 images. It needs to pick which one has the ball in it, or find the crib, or find the cat, right? So these are the right image for each of those different prompts. Importantly, there's no decoder or fine tuning necessary. So the network attempts to relate the words and the objects in the world on its own by learning correspondences between its visual embeddings and its embeddings of the words. And we don't need to train linear readouts or some linear decoder in order to figure out what the network has learned. It can actually produce behavior on its own this time. How does the network do overall? Well, the classification performance was well above chance. So chance would be 25%. And the model with the LSTM encoder for the language can get about 40%. So certainly far from perfect, but nevertheless it's far better than guessing when trying to figure out like which of the different frames has a corresponding word in it for those 26 different classes. And you see there's a lot of heterogeneity if you break down the accuracy by the 26 different classes. Again, looking at accuracy on the y-axis and then the different classes shown there at the top. So you have some good classes like ball is pretty good, car is pretty good, around 60% correct. Sand is very good. So those you can pick out with higher accuracy, but then there's a lot of poor classes like toy is extremely difficult, and chair and cat and so on. So some classes are easier than others. They're also very different in frequency, although it's not a strong predictor of which ones are easier or harder. But a major issue that we're running into now is that these visual classes don't come with a label, right? We just have a collection of cats. And so what word do you associate it with? Well, when we did this, we picked the word cat to associate it with, but it turns out cat was actually not present in the data very much. This particular parent, the parents and the child rarely talked about cats as cats. They talked about them as kitties. So kitty appears 500 times in the corpus and cat only appears 28 times. So the choice of the token you use matters a great deal. And for cat, which gets pretty low accuracy, you do quite a bit better if you ask where's the kitty rather than the cat. So we need to figure out what the right token is to refer to each different classes and see if we can do better. So here are some of the heat maps showing the model's attention. And in general, I would say about half of them make sense and half of them don't. And it's also the model with the isolated word embeddings is clearer and easier to interpret than the LSTM word embeddings. So this is one of the ones with the isolated word embeddings. And when you ask to find the ball, the 4 images on the top are relative successes where it tends to respond, and again, those class activation maps. So the right region, the image is responsible for its classification decision. In this case, it picks up multiple balls, which is nice. But then there's also about half of them are quite hard to interpret. So just to wrap up, let's go back to some of the questions at the heart of what we're getting at here. What is the origin of early knowledge? How much can be acquired through generic learning mechanisms applied to sensory data, and how much requires more substantive innate inductive biases? I think we're just beginning to be able to explore these questions in a new computational way due to advances in the machine learning technology, but also to unprecedented corpuses of data for what children actually see. And what we learned so far is that generic models trained through the eyes of one child can learn high-level visual representations. And these representations are useful for invariances to natural transformations of objects, and also can generalize to novel exemplars in some cases. These representations can support the same types of category discriminations that infants can make. And these networks also show some ability to learn words when trained on multimodal language visual data. Although it remains to see how to build a model that can capture the type of word learning wizardry that children ultimately reach when they start learning 9, 10 words a day, when they start going through an explosion of their vocabulary. There's much more to understand about what abilities are readily learnable through the eyes of a child and what requires stronger priors and inductive biases. So this can include all the abilities in this chart and many others. Can we understand, what types of experiments or what types of data can we explain with massive learning through the eyes of kids, and what can't we? Can we better understand the typical developmental progression in terms of how babies enrich their understandings of objects and agents, how it changes over time, what abilities they get earlier or later, or how they expand their vocabulary? Why is it easier to learn some words than others, or what makes a good exposure of a word for learning? So I believe that this is an exciting opportunity for data science and cognitive science to explore together and help answer some of these basic questions about the origin of knowledge. With that, I just wanted to thank you. I wanted to, again, thank our project leaders on this, Amin Oran and Wei-King Bong, and also thank SACAM for this a truly remarkable data set and its contribution to our work here.
All right, let's give our speaker a round of applause. And now let's open up the discussion to questions. You can either unmute yourself and ask, or if you'd prefer, you can write in the chat.
I'm happy to start if nobody else is jumping on the question. First of all, great talk. Thank you, Brenden. I had two kind of follow-up questions. One was in how you, I'm assuming that the word model in the second part of your talk is based on a manual transcription of some sort, right? Right. And so I guess that that probably forced you to limit yourself to smaller, were you able to use all the data available, or only a subset of those data? I guess my question, I guess there's two purposes to my question. One is, how much data, it seems to me that this is still a relatively small number of weakly labeled data that you're using. And so the question is, how much data would you need? And especially, I would be curious to see what happens when you're in regimes that are closer to the full amount of weekly supervised data that kids get. I guess so. First part, and then the second part is, I would be curious hearing your thoughts about how much you actually need this transcription. And you can imagine doing what you've done just from the raw sound waves, just working from the and directly learning a kind of auditory, visual cross-modal representation.
Yeah, great questions. This is the first about the transcriptions, and we use all the data. So there's 35,000 utterances that were transcribed, about 30% for one child.
Which is not a lot, I guess, right?
Yeah, they're still working on it. It's not a lot. It's certainly something. One thing we could do that would make our lives easier, and that is more reflective of how children will actually see it, is that for each utterance, we just took the frame that was timestamped, that had the same timestamp. But that was actually pretty noisy and not always very accurate. But many of the frames after that are also relevant, right? So we can retrain it by replicating that label across some of the frames after it as well, and that would provide a type of data augmentation that will help quite a bit. But I also heard in your question that perhaps like we pre-trained the vision model, what if we pre-train the language model as well on like a more representative corpus of?
Well, no, I meant on the raw data.
Would that help?
No, more like on the raw data. That how much of this, skip the right? So just on audio data.
Yeah. Well, we did the pre-training on we really pre-trained the language model as well on the corpus, and then tried to learn the correspondences, and we didn't find that helped at all. But you could also imagine like pre-training on child is or some other corpus of language if you wanted to do that. If you want to use the audio, that was also where we wanted to start. Unfortunately, the audio is pretty poor quality on the mics that were used for the data set. So we working with the audio ASR expert Michael Paceni at NYU Center for Data Science, and he was a little disappointed with the audio quality and is still struggling to get some basic stuff to work with it. But we hope we can get there, but unfortunately the audio is not very good.
Thank you.
Are there any further questions? Here's one from Alec. Alec asks, have you tested the networks on ImageNet? Do the features learnt on SACAM transfer over to ImageNet? I believe you might have mentioned something like that.
Yeah, thanks. That's a great question. We did do that too, and the networks are okay. I can't remember the exact numbers, but it was on the order, I think it was better than 25% like top line accuracy, which is actually quite poor for like a ImageNet model today, but it's also not bad given that it's a huge shift in domain, and a lot of the ImageNet classes are completely ecologically implausible for kids, or a lot of them are hard for adults, right? There's, I think, about 120 dogs, different species of dogs in ImageNet. And I don't know that many dog species, right? And it's sort of unreasonable to think that the 12, 18-month-old would know that many dogs. So at one level, I think it's interesting that the features transfer to some extent. On another level, I think we need to look beyond ImageNet as like this, as a gold standard for like, how can we do on ImageNet? I think we should look to how do we do on SACAM, or how do we do on the type of experiences that children actually get, the classes they actually learn from, in terms of trying to understand how our minds develop and how they're able to learn from the data that they get.
And as a side note, Brenden, I don't know if you know about this ObjectNet that was developed at MIT, where this was a reaction to ImageNet, where the idea is to put objects out of context. Everything is pretty much under canonical viewpoint size, etc. on ImageNet. So to try to push the systems on that front. And what's interesting about the work is that they showed that there is no transfer from ImageNet to ObjectNet. And I wouldn't be surprised if your learning is much better, because hopefully there is less of a kind of bias for internet-like photos in your data set.
Yeah, there's a lot of weird views, especially with the younger kids. It can be a little hard in the video to figure out what they're paying attention to. But there's this, working with data like this, we realize so much is different between what babies actually see and ImageNet. And it's more differences and similarities. And initially we tried a lot of different self-supervised approaches, and a lot of algorithms get hung up on the fact that there's just a lot of homogeneity in the background colors. Some rooms have the same lighting, and most of the time you're in the room has this weird purple, yellow lighting, and it focuses on that. Or the seams between the walls and the ceilings are very consistent, right? And in ImageNet, you get a new background for every single image, an arbitrary background. You get this nice centered image, and that's just not what the data look like, what children get. So I think we need to take stock of like, well, what we've done so far in computer vision is really remarkable, but see if it actually works. That's always the problem that the baby mind.
And yet, just and yet, I was just going to add that on there are many cues that are available to babies, right, for figure ground segmentation, such as motion parallax, motion if the head is static and an object is passing, and things like that, which potentially you're not exploiting right now, which should be allowing the learning of representations that are more selective for the foreground in general. So I think there is still, anyway, I guess you get the point that I'm excited about this line of work. I think there is a lot of interesting things to be done.
Thank you.
All right, there are two more questions in the chat that I can see. The first one from Lakshmi asks, how can one get a sense of modality-wise baseline performance for these generic models?
Maybe you can unpack that. I don't know if you have a mic, Lakshmi. But modality-wise, so you mean like how good are we doing on vision versus the
that's my interpretation of his question. But
okay. Well, let's see if they jump in, but
yeah.
if not, I'll answer that.
Oh, he's asking how much of this is from learning generic principles.
Generic learning principles.
Oh, I see.
Yeah. That's a good question. And I mean, that was what we wanted to do here. We didn't want to use additional labels. We didn't want to use a bunch of pre-trained object recognition systems, on ImageNet. We didn't want to use any special visual knowledge, right? We just wanted to see if you take a powerful generic learning algorithm and apply it to a bunch of videos that kids see, what can you learn? Now, there are some assumptions in that, like convolutional nets have assumptions about how useful features are in different spatial locations, but I think the models are definitely on the generic side compared to the range of tools available in machine learning. And that by doing that, starting with generic models and the data and seeing what's learnable, what of those classic experiments with infants, which of those can you get the same behavior out of the models, and which you can't explain, can help us narrow in on what inductive biases we might really need, right? I think the failures of this approach like this are going to be just as informative as the successes. If you can explain some things but not others, it's a good candidate for potentially an additional assumption or inductive bias that our minds might bring to the problem.
Okay, there's one more question. Pachaya says, great talk. Can you briefly recap how you use features from TCs to get the prediction in the first part of the talk again, please?
Yeah. Yep. So we use this sort of linear readout or approach that is pretty standard in self-supervised learning models, where you want to know that I learned features that are useful for classification, but you don't have any labels, right? Like you do in supervised classification. So how do you do that? What you do is you train one of these deep models. So with the ResNet 50, that's 50 layers. And then we freeze the trunk. So none of those features are allowed to change anymore. And all we do is say, can I discriminate cats versus dogs, hands versus feet? Can I discriminate those 26 different classes? If I train a linear classifier like logistic regression on top of the frozen trunk, so can I discriminate those different classes just with recombinations, weighted recombinations the features already have? So you're not learning any new features, you're just seeing if I weight this feature by this much and by another one by this much, can I make the discriminations that are necessary? Which I think is actually not too different than what infants might be doing in those experiments, like differentiating cats versus dogs or dogs versus birds. In a lot of those cases, it's not clear for the 3-month-old if they know what a dog is already, or if they come into the experiment and you show them 12 dogs and they get bored, you show them a bird, that they just learn that distinction on the fly there in the experiment. You don't know if it's pre-existing or not. But I think it's not crazy to think that they have these generic high-level features and that they're sort of learning a discrimination on the fly with like a simple model in order to make predictions in the particular environment that they find themselves in. So I see it as a little bit like that.
All right, maybe time for one more question. There's one available. All right, well, in that case, let's thank our speaker one more time for a great talk. And thanks everyone for joining. There are more talks that you can find on the website, and we hope to see you there. Okay, thanks everyone for joining.
Thanks for listening, everyone.
Yes, thank you.